The real world is chaotic and impossible to capture in its entirety, which is why we need a new open foundation for physical AI. This episode packs several deep dives, moving from preparing Blender scenes for robot intelligence to exploring how Japan's philosophy of excellence shapes modern algorithms. We'll also uncover how India is building its own AI future and see why autonomous agents are now accelerating the design of the chips that power it all. Let's start with the very first step in making machines understand our physical environment. The real world is chaotic and impossible to capture in its entirety. Physical AI systems need vast amounts of data, but collecting real-world footage at scale is a logistical sculpture. That is where NVIDIA Cosmos comes in. It turns raw compute power directly into high-quality data. This opens solutions for new architecture that processes pixels, actions, sound, and language all at once. It uses an autoregressive transformer to reason and plan, instructing a diffusion transformer to generate the next logical frame in a sequence. Developers can post robots and environments across countless different train observer is evolved as a vision language model. It acts as a keen observer, watching the physics, describing complex scenes, and flagging critical details. But it goes further. As a world model, physics-aware synthetic video from simple text or image prompts. Cosmos functions specific actions. Cosmos functions as a simulator, inferring what happens next and generating plausible future scenarios. This closes the loop for training. It evolves into a world policies by post-training the model into a world action model. It can perceive, reason, and plan for any type of robot moving in any environment. It generates actions for everything that moves, creating a new kind of data and a new kind of teacher. NVIDIA Cosmos represents the frontier of physical AI, offering an open foundation model for developers ready to build the future of autonomous. Since the real world is too messy to model directly, we have to turn to simulation where the future of physical AI truly begins. The future of physical AI starts in simulation. Before robots navigate the real world, they must first master synthetic environments, sensors, and material properties, not just their visual properties. Which is This is where Blender meets advanced simulation tools to create a bridge between digital design and robotic action. Developers are now using Omniverse libraries to transform standard 3D scenes into robot-ready environments. The process begins with the OV Physics Library, which provides real-time, GPU-accelerated rigid body dynamics directly within the Blender viewport. This allows for accurate tests interact, fall, and collide under realistic forces. Simultaneously, OV-RTX technology brings high-fidelity sensor simulation into the workflow, enabling the testing of LiDAR actual and camera data as if the robot were actually present. The workflow is designed for validation. AI agents can automatically scan a scene, check for missing information, and update the digital twin to ensure it matches physical reality. Every tool and every scene is rigorously validated to guarantee that the simulation behaves exactly like the real world. Once a scene passes these checks, it is fully robot-ready. This seamless integration allows developers to move their validated scenes directly to Isaac Sim for further training and deployment. Teams can accelerate the development of autonomous systems by ensuring that their robots are prepared for the physical AI era before they ever leave the digital workspace. Simulation gives us a controlled playground, but to build anything great there, we need a mindset where true excellence is a philosophy of life rather than just luck. Japan has long been a teacher to the world, proving that true excellence is not accidental but a philosophy of life. At the heart of this approach is Kaizen, the relentless practice of improving visible processes on the shop floor. By constantly refining manufactured made in Japan into a global symbol of quality, beauty, and imagination. This spirit of craftsmanship extended beyond the world of designs via hardware, evolving into the world of video games. Through art and storytelling, Japanese creators captivated generations, bringing robots to life and changing the very fabric of reality. This evolution eventually led to a pivotal partnership. A project named Dreamcast was launched with the belief that a new generation of gaming consoles could be built together. However, the initial approach was flawed. Recognizing the mistake, the team sought to be released from their contractual obligations, a request that was graciously accepted. This error in judgment gifted the team with something invaluable: time. That extra time allowed for the invention of the GPU. the essential component that would enable the next leap in visual processing. From that moment forward, the collaboration between the GPU architecture and Japanese innovation began to reshape the world once again, turning a simple manufacturing lesson, a foundation, into a foundation for artificial intelligence. That philosophy of deliberate improvement has long been taught by Japan, yet similar rigor is now being applied across the globe to build massive government-backed AI initiatives. From a small academic consortium led by IIT Bombay, starting with a call for proposals, the team was selected to build small models up to 10 billion parameters with significant over in 2 years. The vision quickly expanded, aiming to develop models up to 1 trillion parameters. Initiative up to multi-million parameters. Today, the initiative has launched a suite of multilingual models, officially Talclaticus Pentuitu Dilatime Acresitu. These models make medical information easily comprehensible for patients. In education, partnerships with organizations like the Quote Education Foundation use AI co-pilots to help student applied. Assessment effectiveness is also being applied in finance, patients' effectiveness. The technology and sanitation effectiveness. The water and sanitation to ordinary citizens. To make complex data accessible to partners' environments. The Rilakal Kausats Ahiaplot Commodamary citizens. The collaboration moved from early cycles using Megatron to leveraging the Nimatron ecosystem. With Vidziat's open source approach, which values dialogue with as much mod intelligence, which values dialogue as much as code, proved vital. Specific tools like Nimo 2.0 for pre-training and Nimo RL for post-training allowed the team to scale their models across multiple nodes. Observability and development flexi and throughput were kubitas and flexibility were key learnings from working together. The partnership extends beyond training into inference, with ongoing conversations to build even larger the wheel. BharatGen strengthens both its internal capability, serving as a Atlas Ashes and the broader open source community. This collaborative approach, ensures that the technology continues to evolve, serving as a catalyst for learning and innovation across India. As those global initiatives scale up, the race to construct the next generation of AI factories heats up, revealing just how incredibly complex the underlying chips have become. The race to build the next generation of AI factories is heating up, but the chips powering them are the same rigorous path design, verification, implementation, and sign-off. Every single chip follows the same. The systems they run must meet relentless demands for performance, power, area, and thermal efficiency. Hundreds of engineers spend months working toward one goal: first-pass silicon. The solution? Autonomous AI agents managing the entire electronic design, automation, and systems engineering stack. At the design stage, cadence is autonomous from weeks down to hours, even driving the development flow itself. Moving into verification and autonomously handle implementations deploys a broad set of agents to Anopsys deploys of the transition from RTL to GDS, all under human supervision. Their Prime Sim Spice tool accelerates simulation up to 18 times faster in Prime Sim. During the sign-off phase, Siemens Fuse EDA AI agent performs autonomous physical verification. Next, AuraStack AI unifies 3D IC packaging and PC design, managing the process from exploration through physical implementation and final sign-off. Beyond the chip itself, NVIDIA COO ISS agents utilize NVIDIA Physics NeMo to predict fluid, thermal, and structural behavior. Synopsys extends its reach from EDA into system design, bridging the gap from silicon to systems, all accelerated by NVIDIA ISS. Fewer iterations mean engineers have more time to invent what comes next. This is how next-generation chips are built with NVIDIA technology, ensuring they are designed, verified from at the speed the AI world demands. With chip complexity reaching new heights, the gap between abstract AI concepts and real-world market leadership is finally closing fast at NVIDIA GTC Taipei in T2026. Welcome to NVIDIA GTC Taipei in 2026. Today, sophisticated startups NVIDIA stacks to tackle complex startups are using the full NVIDIA stack to tackle complex challenges across every industry. These pioneers define the frontier of physical and sovereign AI, bridging digital intelligence with real-world infrastructure and fluorescence science through breakthroughs in quantum classical 5G, Hapshian 6G connectivity, and precision science. First, meet Tricos-Coco Research and physics AI models to accelerate the entire R&D lifecycle. By running physical calculations 1,000 times per percent faster for physics and pairing some cheap Cetrel 7 calculatives, they cut experimental need statistical algorithms and compress weeks of research into minutes. In healthcare, the finding stack leads Taiwan with Hepatowell AI. Powered by a 3D deep learning model, this platform achieves a DICE score over 90%. It ensures high-precision volumetric liver fat fraction analysis, even when motion artifacts are present. Finally, for physical AI, Nexuni leverages the NVIDIA Isaac General platform. They are developing applications for complex environments, proving that the next industrial era is already here. Thanks for hanging out with me. If you found this breakdown useful, hit that like button, subscribe, and ring the bell so you never miss an update. Catch you in the next